It's evening. Dev and Mohan returned home after shopping. Mohan switches on the fan and bulb. As he saw that 2 bulbs are on, he switches off 1 bulb. Dev was watching this carefully and thinking of something. Then Dev said to Mohan that when you switch on the bulb, it doesn't glow instantly. And also, when you switch off the bulb, it doesn't diminish instantly. What is the reason behind that? Mohan told him that it is due to the induction of current. The induced current always tries to oppose the course of change. When bulb turns on, then an induced current develops such that it tries to remain off. Similarly, when bulb turns off, then an induced current develops such that it tries to remain on. That's why the bulb doesn't glow and diminish instantly. Students, electromagnetic induction is everywhere around us. We use many appliances or applications that are based on it. So today we have objectives. At the end of this lesson, you'll be able to define electromagnetic induction, understand the experiments of Faraday and Henry, define magnetic flux, understand Faraday's law of induction, state Lenz's law and conservation of energy, define motional electromotive force and energy consideration, define eddy currents, calculate mutual inductance and self-inductance, describe AC generator. Definition. In our everyday life, electromagnetic induction plays a vital role. Transformer, generator, train, and telephone are some examples which work on the principle of electromagnetic induction. An electric current can be produced in a circuit by a changing magnetic field. The current in the coil brought about by a changing magnetic field is called an induced current and is said to be set up by an induced EMF in the coil. The phenomenon of producing an induced EMF with the help of a magnetic field is called electromagnetic induction. The experiments of Faraday and Henry. Experiment 1. Consider a bar magnet that can slide back and forth along the axis of a helical coil of wire to which a galvanometer is connected. When the magnet is at rest, no current is observed in the coil. The magnetic field at the coil is not changing. When the magnet moves towards the coil, a current flows in the coil. As the magnet approaches, the magnetic field produced by it at the location of the coil increases. When the magnet moves away from the coil, a current is again produced, but in the opposite direction. The magnetic field at the coil decreases. We conclude that only relative motion between the magnet and the coil is required to produce the current. Experiment 2. Consider 2 coaxial coils, one called the primary coil P, connected to a battery via a key K, and the other called the secondary coil S, connected to a galvanometer. When the key is closed, the galvanometer in the secondary circuit deflects momentarily and then returns to 0. The magnetic field at the secondary coil increases from 0 to a steady value. When the key is opened, the galvanometer deflects momentarily in the opposite direction and again returns to 0. The magnetic field at secondary coil decreases from the steady value to 0. The galvanometer reaches 0 when there is a steady current in P. Here the magnetic field at the secondary coil is not changing. Magnetic flux. It is a measure of the quantity of magnetism, being the total number of magnetic lines of force passing through a specified area in a magnetic field. If a uniform magnetic field B acts perpendicular to the plane surface, then the magnetic flux through the area A is given by the product of B and A. If the magnetic field B makes an angle theta with the normal to the surface, then the magnetic flux is given by BA cos theta. Or it can be written as phi is equal to dot product of B and A. Magnetic flux linked with a closed surface may be defined as the product of the surface area and the normal component of the magnetic field acting on that